Hello guys. I would like to start with my presentation. We finished project that is related to Thatcher agency, grant agency, and we developed their software for aircraft maintenance. So for MRO organization, mine maintenance repair operations organization. It is software for planning and execution. Of course, it's a knowledge-based system. And the idea of this presentation is to describe you a little bit those use cases and the system itself, but mainly focus on selected challenges and how we dealt with it, and what were the problems, and how it could be solved, or what are the future research ideas how to solve problems like that. So the presentation is separated into three parts. In first part, I will describe the system a little bit, and then I will show selected challenges, and then I will show you a live demonstration of the system. Unfortunately, this shouldn't be shared because it's a live system, so we need to stop presentation there when demonstrating the system. So just to explain the use cases, we have CSAT, which is organization to maintain, to repair aircrafts, and their goal is to repair or do the maintenance of multiple aircrafts in their hangars, and for that they need to do planning very well. And the planning consists of on each aircraft typically at least 50 people at same times are participating, so it's quite hard to plan such a maintenance. And within the maintenance there are multiple roles playing, and one of them is somebody called strategic planner, who is communicating with client, and he decides how long it will take. So based on history of how long it took, he decides a time slot in which the repair or the maintenance should be done. Then there is some kind of planner. The planner is a guy that make a plan, which tasks will be done first, who will participate when, and so on. And then there are some mechanics who are executing the plan. And for one more interesting thing about the maintenance is that the most important tasks are the tasks that can that are called findings, and those are unexpected tasks, because usually maintenance is done according to some manual. So whenever a client asks for doing some task, it is usually clear for 80 or 90% of tasks. It's clear what to do, but while doing those tasks, some findings could happen. For example, a corrosion of some part of the aircraft could be there, or something is not working well, it's old or something. And those tasks are most important, because they can prolong the period how long the repair. They are unexpected, and they, for example, you need to buy a component and put it there into aircraft. So for this reason, we focused on findings, and it's this part which is done by system, which is trying to analyze findings from history and current findings and evaluate how long they could take. Those findings are not tasks that has some kind of ID that could identify what will be done. They are just texts that people write. For example, I found corrosion there and there while checking this and this. So we have this input from users, and we are trying to see how long similar tasks took in the history and what are the issues, what component, what failure is there, so to find out whether the component should be ordered or something like that. This we created, I could say, 3 parts of the software. One of them is to create plans, and this is some kind of calendar where here on the left there are some resources. They are hierarchically ordered, and here are some different tasks. It's planned on different levels, from big task like phase 1, phase 2, phase 3 of aircraft, where phase 1 is some repairs, phase 2 is checks, phase 3 something else, or it's those tasks done in manual, so following task in manual, or the even lower level is those concrete sessions that people are doing, so those concrete repairs of one person. So there are different levels how this is done, and you can see that we are calculating some kind of estimations, how long it should take from history and so on. So this is one part. The system allows to really create a calendar of what will happen when, and also keeps track of what already happened. So this was related to planning, to support the planning. And to support execution, we are doing some kind of dashboards that evaluates how well are those mechanics working, or how well we are going according to plan, and so on. So those are some kind of dashboards. And the third part is analyzing those findings that I was mentioning. So mechanics, whenever they find something, they write what happened, and we are trying to analyze each finding and make some kind of clusters of similar findings, and based on history we are able to evaluate how long those findings could take, or what dependencies it has on components, for example, and so on. So this is the last part. And so that's all. I wanted to just show it very briefly. And now I go to some challenges that I mentioned. So one of the challenges were data processing. We had inputs. We were basically looking at system at Czech Technics as black box, which was generating us some kind of views on their database using CSV files which were uploaded to FTP. Those are different CSV files. So, for example, time analysis file is logging which tasks were done, when it happens, and so on. Time estimate is estimations of those tasks which were done before that. And then, for example, presence is log when employee is in workplace. So when they come to place and they leave, and so on. There are multiple types of those tabular data. And they are, of course, not normalized. They have many issues that I will do later. There are also some kind of more stable data which are defined only every month. Those data, as can be seen here, they are uploaded twice a day, or some of them even faster, and so on. So they are uploaded to FTP with different pace, and they reflect some part of the database, so not full database, only part of the database, and not through whole time, but only through some time interval, I would say. And then we have, of course, some RDF data, for example, formalized aircraft maintenance manuals or manually computed statistics from data. I will go further with these CSV files, and this is how they look. We use Google Documents. As I said, for us, the database, the system it came from, so data sources were black box. So we asked our domain experts to annotate those CSV files that we retrieved, and we made many assumptions that what the data are. So, for example, what are private keys, foreign keys, and what is whether the field is required, whether it has such values or so on. We used S-pipes to implement the pipelines to transform CSV to RDF. Of course, it was nice to use S-pipes because we could formalize those constraints that we assumed in CSV files by some integrity constraints. So, for example, here we say that column duration full cannot have empty value, and so on. So S-pipes was interesting for that. And then we needed to represent, to collect the data and represent it in our database. So what we did is, here we have some kind of time, and the system at CSAT decides when it upload the files into FTP. We check it periodically, and then we just whenever there is a new file, we process it and we create some kind of snapshot of this part of this data set, I would say. So, for example, here you can see that at February 2nd, 5:03 in the morning, the time analysis CSV and time estimate were added to FTP, and we just process it through S-pipes and create a graph within our database that collects the whole history of the system, I would say, whatever was put into FTP. So this is complete history of what happened, and within those snapshots, there could be some entities, there could be some events like UFO events or UFO entities. So some of the things can stay as they are, so they are not modified, but some of them are changing. So, for example, some user wrote a text what happened, but then he figured out that it wasn't precise, so he rewrote the text or something like that. Or somebody did estimation, but then he decided to do better the estimation of the task or something like that. So one of the problems was first to collect all the changes, but then somehow to consolidate or somehow to combine those data and decide which things are changing, which are not. So we need to, after extracting each data set and creating such a history, we had to go over the history and decide what is the last value, I would say, or what is the current value of what is the current state of the system. So we need to identify which properties are unmodifiable, I would say, and which properties are changing, and so on. So the challenges were related to quality of input data, as I said. There were denormalized data, there were redundant data sometimes. So in CSV file, you would see same row twice or something like that, or redundant attributes, so they were inferred. So for example, you had start date, end date, and then computed value, or which is duration. There were a lot of missing incorrect data. For this, private keys and foreign keys, for this S-Pipes was quite good to process the data and put those integrity constraints in there, what is in the input. The other challenges were to combine the data, as I showed you in the GraphDB. We wanted to have ability to recompute some parts of data. So for example, when we would extend the transformation, we wanted to recompute only, let's say, last month, or I don't know, last year or something like that. So this is why we created this this format, how to store the data, that every data set is has some timestamp when it was created, and it has reference to the dataset type, I would say, and those are ordered, and we can always say, for example, if you see time analysis snapshot here and time analysis snapshot here, that we can always say that if here is new value, it overrides this old value. So for example, if some value change, for example, time estimate of some task, then this is value that should be taken for granted. So you could to compute what is the current state, you could take all change properties and diff between a data set that comes before the data set itself. I hope it is clear. So this way also allows us to, if for example, system stops working for one day, we can still run the system and it will generate those snapshots, and we can anytime we can add those missing snapshots in there or recompute them, as I said. But what it caused is that we had quite many triples generated from CSV files. So for example, 406 million triples for a period of 3 years. And most of it, as they really are representing some part of the database from some period, and this period was like the time window, and it was just moving, and the data were taken from this time window. So what happens is that a lot of data were the same for every context, for many contexts. So for example, here, this time analysis context would have very similar data to this. So what we need to do is do the duplication. So we just removed all the triples that from older data sets. So again, going back from this data set, we removed all duplicate triples that are occurring here. This way, we got history, which has almost the same expressivity. We almost did not lose any information. Almost. We are not sure, 100% sure, when value was created. So when so if here is, let's say, some time estimation, and this is here is same as the time estimation, we removed it from this one. But so we don't have anymore the information where the information was created, but we can still compute what is the current snapshot of the system. We can see when a value changed. So if there would be some value and here is a change value, then you would see the triple would stay here and here. So we have the history. And we can recompute again different parts even after, and deduplicate again. So this was one interesting operation that we were using to optimize it. And as I said, there was need to create a last snapshot of that data. So to go over all the graphs and leave, see which of the values are conflicting. So let's say, as I said, task having time estimate, task having different time estimate, and we always had to leave only the last value of such conflicting properties. So those were the challenges, and the other quite big challenge was to have this history and combine it with online data that we were generating, because we had it in different RDF4J repositories, and for RDF to process two repositories with 400 million triples, it was quite slow sometimes. This is why we, for example, did the duplication. What could be improved? Just to summarize, as I said, S-pipes showed us that they are quite useful for processing the data, but they had some issues. We used tabular model, but for big CSV files, it was quite ineffective. So, for example, we had files with presents, and they started to send us a file that would contain 200,000 lines, but we really wanted to process only part of the file. And currently, the tabular model within S-pipes does not allow filtering before serialization to RDF. So you need to really load all the file into RDF and then filter it. So this is something that we could improve. Then optimize custom Sparkle functions. When we were processing the files, we used Sparkle construct queries and our custom Sparkle functions, for example, add date, which takes date and add one day to the date. So this is custom Sparkle function, which could be used in filter, for example, or somewhere else, in bind and so on. And this we experience that there are a lot of performance issues related to that. You really need to write those functions carefully. We experience some garbage collection issues in sense of too many garbage collections were done sometimes. So this is one thing. Also, we experience that SPIPES needs quite a lot of memory, and it runs quite fast when it has memory, and it runs very slow when it doesn't have memory. This is related mostly to the point before that. So there is a lot of garbage collection when not enough memory is there. We also use IOPA to build tabular model, and it doesn't support blank notes yet. So this would be for the processing of CSV files. We represent the data using blank note, schema of the CSV file using blank notes, and this support would help, which might be coming, not sure. Then what could we do? As I said, the very hard task was to find out what CSV files they are sending us and what did mean, and when it can change, when it cannot change. And this can be very well computed from history. So we could query history of converted CSV files to find out how the system behaves, so what properties are changing and so on, and then put it as integrity constraints into the pipelines. Also, the creating last snapshot of the system could be done from the integrity constraint itself. We were doing it some kind of separately. Another thing is that use of shackle integrity constraints are nice to express, like ask queries, like you could see here. We can also use select queries, which would even point you to the concrete data where the integrity constraint fails. But what would be much better is to use shackle, for example, to represent integrity constraints, which we could also use maybe as integrity constraint for IOPA models in future. I don't know. Then the last interesting point was that we had issue with speed, as I said, to create 406 million triples and to deploy it to GraphDB and so on takes some time. When you're doing it as a batch operation, which we needed sometimes, it really takes a lot of time. So it was interesting to consider even the duplication on CSV instead of the duplication on RDF. So do it before. So that's for data processing. For text analysis, I will be very short. So the main goal was to be able to find components and failures within the text. And what we did is we used Termit for domain expert to annotate components and failures. And then we create a SPIPES pipeline that would annotate new texts. And those texts were search for component and failure. And based on this tuple, we create clusters of those tasks, and we could say that this task is very similar to this, and that's why from the history it applies that it will take, for example, 5 hours because this and this. So this was the idea, but the problem is that those texts are having issues, of course. So, for example, people write acronyms, they make mistakes and so on. We use hidden labels. And another issue was that on one line, sometimes there were multiple components mentioned, and or multiple failures, and we need to select only those important ones. So for that, we use some kind of knowledge rules. Here is knowledge rules which we use in pipeline, for example, or a similar one. So if you find in text a component 1, component 2, and you find a failure, and component 1 is part of component 2, and this failure is missing component, then just infer that the failure, that it is failure of first component. So to say what happened here, if you have that something is missing, and so in cabin there is missing chair. If chair is part of cabin, so usually when you say something like that, if you see this pattern, you really mean that its chair is missing and not the cabin is missing. So so that's why such a rule. So this is something for the future work. The text analysis. Oh, sorry. Text analysis from Termit was not that useful. It is meant for different use cases, so we somehow abused it a little bit. It's more for the search of terms, definitorial terms and stuff like that. Not for search of data, I would say. But it got us quite good enough results. But it would be nice to really try those machine learning techniques. For example, takes those concepts, takes those labels, find it in language models, represent those concepts as vectors, and try to do the same analysis of text with such vectors. Another thing for clustering is just we could take whole text and make vector representing meaning of the whole text, and just see if those texts are somehow similar with respect to meaning by those vectors. So that's text analysis. And the last part, which will be fast, is how we try to make development and deployment more effective. We did automatic deployment using GitHub hooks, which we did in other projects, but here, in addition, we are able to refresh the orchestration as well. So even if you change a Docker Compose file or something in this main Docker orchestration repository, it could be updated automatically. Then we used for logging, we use Grafana, and based on that, we are able to notify when something bad happens. This was particularly very important when some integrity constraints failed, that we could find out. So we could change the pipeline. So if you don't know the data, for example, like we didn't, then it could be useful. The last challenge was that it was quite that the model was changing quite a lot, and to propagate all the changes to all the software parts and everything was quite hard. So maybe I will get back to this. So this is how the update is done through webhooks. I just say one thing here, that the solution is in a way that we have some kind of Nginx reverse proxy that is linked to var run Docker sock and is able to restart Docker. So whenever something happens, it can restart. It can do basically Docker Compose up, Docker Compose pull, and so on. So it is complete solution. You don't need to put any any processing in front of the application, the whole application can be deployed and it will work with webhooks. So this is what I wanted to mention. And the last slide is about using Grafana. We are using Grafana, which is log viewer, and that uses Elasticsearch, Fluentd driver, and these three things, Elasticsearch, Fluentd, and this Grafana is combined together, and through that you can see the logs. And based on logs, if something happened, you can trigger some notification, for example, Slack notifications. Yeah, and for the future works, as I said, we had quite issues related to model changes. It would be very nice if we could use for modeling assembly line that we are developing at KBSS, or the Termit ontographer and the tools related to that. This would quite help. That's all. So thank you. We should maybe please ask some questions, and then we would go to demo session, which unfortunately has to be private.
Okay, thank you, Miro, for the presentation. It looks like it's quite robust all the way. And I just wanted to ask you, so that there is a lot of triples, and those triples basically represent data, and you were talking about some conflicts. So it means that there is some validation of the data based on the ontology, or how is it done?
Mm-hmm. Yeah, so you're talking about this. So yeah, we have some kind of constraints. Yes, we have constraints represented in IOPA. So we are using, for example, in Java, we are using IOPA models, and there are some constraints on the data. So for example, as I said, task can have only one time estimation how long it will take. So we will find out those constraints there in IOPA model in Java. And there are constraints like ask queries or select. We have select or ask queries, which are representing those constraints as well. So for example, here you can see, as I said, that duration full must not be empty. This is constrained on CSV level, but then we have also constraints on the domain model. The similar constraints, they are in the pipeline. So whenever you transform something, you then check that it is okay. But what I was mentioning there, ontology itself is not that useful for validating. I mean, harder to use for validating, but what would be even better is to use shackle, which we could shackle constraints, which we could apply in the pipelines as well in the IOPA. IOPA doesn't support shackle yet, but I think it is planned according to Martin. And SPipes also does not support shackle yet, but we are planning it as well. So this would be the best to have these shackle constraints, use it for within the pipelines, and the same constraints use it for generating IOPA object or for validating IOPA model. So
if I get it right, it's something like on the transformation side from the CSV to the RDF. There is some validation which is done basically that after transforming data into RDF, you just ask some prepared queries.
Yes.
And you're asking, so if everything is no, then it's valid or something like that. Okay.
Yes.
Yeah. And if we use Shackle, then it would be easier that the data which are not valid are not uploaded into the data store.
Yeah, Shackle, the difference between Shackle and Ask queries is that you can reuse parts of the shapes, Shackle shapes, and you can combine them better. And if we have support within both tools, we could reuse those Shackle constraints as well. So this is just different way how to represent the integrity constraints. Shackle is more appropriate, I would say, for the validation. But we don't.
Okay, so there is no validation that the transform data are according to the ontology or something like that. So
There is.
Yeah.
Whenever we are doing this, when we want to make it consistent, we just we have update queries which make it consistent, and those update queries, the where clause is basically the select query, which or is basically ask query, which is the validation constraint. So we have those validation constraints which are ask queries, but not only this, we have update queries which make it consistent, and they make it consistent in a way that they will remove triples from older data to make it consistent. Is it understandable?
Yeah, okay. So you are basically transforming the data again. If they are not consistent, the triples which are not consistent are removed.
Yes, they are not consistent only in situations where object changes and we want to have only last snapshot of the object. So
Okay,
let's
so does
say,
it happen often that the data that are already transformed from the CSV are edited afterwards?
yes, but it's not only about editing, but yes, they are edited quite often. But it also can happen that the relationship between two objects is updated, or age of aircraft is something that is naturally updated, for example. Yeah, there are some properties that are naturally updated because of
And
time
they
or
were,
because of something
yes,
else.
and there may be some other case that you update the ontology. So this is also the case. You update the ontology, and some of the data which are already there are not consistent anymore. So is this the case, or?
Yeah, this is something that we don't have really solved, that we update ontology, and to have an efficient way how to refactor everything, we don't have solved. But we usually had rather additional changes, or I don't know how to say it, additive changes instead of breaking changes. So this is not
Okay,
an
okay,
issue,
that makes
but
sense.
even those additive changes are quite hard to propagate to all the modules.
So
And
that means that there has to be some methodology on how to update ontology to do not make some crashes in the past.
sure, yeah.
Okay, thank you very much.
Mhm.
Do we have some other questions? Because if not, I'm stopping the recording so we can see the demo. Okay, does it look